I think, well, first of all, welcome. And for the last 11 years, I was a professor here, but I come and go. I'm an adjunct. So this year there was a minor crisis, but anyhow, I'll probably be back next semester teaching here. But what this is an interesting subject because, well, the usual successes I have in the speech this afternoon. So I'm giving 2 speeches on AI. The second one is specifically machine learning, embedded systems, machine learning. And why I put that together, I had that together for our IEEE group and gave that, what, 2 months ago?
21st.
Yeah. So that's really where the activity is in AI, which is embedded machine learning. So that's a speech I'm giving this afternoon. So while I was all set to go, I'm thinking, well, you know, I've had a number of disasters in my life, and I started thinking about, yeah, well, it was initially a sad story, but then again, from sad stories you learn things. So what I've learned is what doesn't work with AI, and why I call that epic is we'll get into that. But anyhow, so I'm going to analyze 2 huge systems. One that dates back from the early 80s, which is called MYCIN. MYCIN is the tool. MYCIN is the product with loaded knowledge. And I'm going to talk about WATSON Medical. This is, if everybody knows WATSON, we're going to talk about the amount of money and time that went into both of these. And I went to independent sources to find out what works and what doesn't work with these 2 products, MYCIN and WATSON. So we're going to get into that, and I'm going to analyze it, which is interesting because some of the things I've come up with, I haven't seen on any of the peer-reviewed literature on this. So this is what we're going to talk about. Why epic? Why do I use epic? Well, AI failure in MYCIN was particularly hurtful for me because I'm sitting in the Carnegie cat hospital and my Molly was dying of a bacterial infection. Okay. And so that's one of the things. But so why was Molly dying of a bacterial infection? You know, we have antibiotics. Well, guess what? You don't have that many antibiotics left, by the way. In some cases, we'll talk about that they don't work at all. But in this particular case, the same treatment and the same diagnosis was done on Molly as it was done on my mother, my sister, and my father, which is if you have somebody in your family that has a bacterial infection that you pick up in a hospital, MRSA, or any of the very common bacterial. In my father's situation, we're going to get into that, but he had a bacterial pneumonia. So to diagnose that, here's the crazy part. It takes 3 days to diagnose it. And I'm going to get into that. And so that started triggering about why this long duration. Most people, in this particular situation with my cat, I didn't have 3 days. And they sent it out for analysis on, you want to identify the bacterium and you want to identify the type of antibiotics that still work on that strain. So that's the detail I'm going to get into. But either way, it takes 3 days. So at Carnegie Cat Hospital, which is normally pretty good, they decided that they didn't get the results in 3 days. So I waited 7 days, and the cat was gone in 7 days. So and anyhow, so that's why I call it epic, because it's affected my family. It's wiped out most of my family and my cat, you know, which is important to me. So then I'm going to get into the technology of MYCIN, and in the, like I said, in the mid 80s, 84, expert systems was the rage, and I'm going to plot where that's gone and what's happened in that area, and the good, the bad, the ugly, I call it. And so that's the 84 large expert system was to diagnose and speed up the diagnosis of bacterium infections and to identify the bacterium. And I'm going to go into detail of what the experts say the failure was. And then I'm going to add my 2 cents worth because of my experience with embedded machine learning and what's missing in this kind of system. So anyhow, that's why I call it epic effect in my own family. And MYCIN was a tool designed to diagnose bacterial infections and meningitis. Later on, they added meningitis and some other rules that we're going to get into. Okay, so jumping fast forward to 2011, IBM Watson. Everybody here with Watson? So we're going to go into that. That's large language models. That sounds familiar. It's still supervised learning, like we're using today with the newer systems, but and then lessons learned. Okay, so let's talk about Molly again. I think I told you the painful truth. So they told me it's going to take 3 days to get the results back. At the end of 3 days, no results back. At the end of 7 days, 6 days, I got the results back, and the cat was with bacterial infections. Specifically, they diagnosed this was a strain of E. coli that she picked up, probably from drinking bad water outside. She's the one cat I have in my family that I allow outside. Turns out that's not a good idea. But anyhow, so the test, the basic fundamental bacterial test and associated identification of the proper antibiotics takes 3 days. Okay, so this got me to think about, with all the work I did now. Well, we're going to get into this, but anyhow, so poor Molly, after 6 days of not knowing, multiple organs shut down, creating agonizing death. Not good. So here's what's really, in a sad way, interesting. So my father died of bacterial pneumonia. It was untreated. He got out of Princeton Hospital and came home and died. And he had bacterial infection, and they made no attempt to even run the culture that they normally do. So he didn't have 3 days anyhow. So maybe they just sent him home to die. I don't know. My mother had a UTI infection, and the assisted living place didn't identify it for that she even had an infection, UTI, for 7 days. Now, we have a few women in the class. The UTI infection, if you let it go for a week, your organs start shutting down. So my mother died basically of untreated UTI. My sister was involved with a transplant, and she picked up a bacterial infection. One thing about a transplant, and this was a bone marrow transplant because she had leukemia. One thing about when you go in for any kind of transplant, you have to be in a clean room, in a bacteria-free, pressurized room. And you have to wear a gown if you're going to go see a person in that situation. So I get the call, she's dying, and she has a bacteria infection. Somehow she picked up a bacterium in a pressurized room. And so then I insisted on speaking to her doctor, and I went through the whole procedure and the differential diagnosis of what the doctors do and how they get results on any kind of infection. And so here's the bad news. Now, we've been running out of antibiotics. What's interesting, if you go back to the original MYCIN system, they have for example, penicillin in the rules list. If the series of rules, and several of them is apply penicillin. Well, penicillin in 2024 doesn't work at all. So don't if you have penicillin in your drawer, throw it out. It's not going to work anyhow. So here's the message in terms of antibiotic front. Assuming you can identify what antibiotics work, which is getting harder and harder, but assuming you can identify the specific antibiotics, a lot of the big pharma is not working on antibiotics, just not working on it. So here I just got this news clipping from the New York Times where they announced that first antibiotic for a gonorrhea, but it's first to be developed in decades. So you got one new antibiotic in decades, you know. So this is the kind of rate at which we're producing new antibiotics. Not good. And in fact, the development of it was done with a nonprofit group because the big majors don't see a profit in antibiotics. So you know, that's the first thing. Okay. So here's what's interesting to me. So what would be the definitive lab test to diagnose MRSA? So MRSA is very common in hospitals. In fact, if you go in a hospital, first question you should ask is, what's your MRSA rate? Always ask that question, because you may be shocked and you might want to leave that hospital immediately. MRSA is very serious. And right now, here's what they do. So the lab study, and this is what you'll see in common identification today in differential diagnosis. So what they do, they'll send out a blood sample. And what they'll do is to take the blood sample and grow it in a Petri dish. The same Petri dishes that they set up for identification of the bacterium, they have pockets of antibiotics, cool pockets where they can put different antibiotics. So at the end of, well, they talk about, if you go down to the bottom here, you got the control, incubation, and results. So this is what they're doing in the lab. So they're taking the sample and they're growing it, and they're identifying what type of Staphylococcus it is, Auris ATCC. So this is they have a control group to do that, and then they have, next to yours is the control. Next to that is the pockets of antibiotics that they're going to try on it. So what you see if you have colonies turn black in the Petri dish, and then next to that, next to the antibiotics, you might have a little circle, a little radius of clear, a clear to opaque that's changing the density of optics. So what that means is that antibiotic may be the one you want to give. If it's cleared up on a Petri dish, it's what they prescribe. So this is what they're doing right now in the lab. Different labs we have in this area. This is a normal thing. So they grow it on. Once I was able to establish what type of agar plates that they're growing it on, then I went to the source of the plates, and I got a little bit more information. But anyhow, there's an incubation time. But notice the incubation time, 18 to 24 hours for each one of those for MRSA. So you're sitting in a hospital, you're diagnosed with MRSA. They run as fast as they can, they run the sample over to the lab, and the lab's got to grow it in a Petri dish for 24 hours. That's before there's anyone looking at it. So they manually look at this thing and determine, gee, what works? What is the bacterium? And hopefully there's some antibiotics that work. If not, they repeat the test. So they got another 24 hours to test other antibiotics if they come up with 0. And let's see. So I did a quick screenshot of the actual test environment and their reagents that they have for the formula for growing bacterium. So this is like the ideal for the glycerin and milk casein, sodium pyruvate, beef extract, lithium chloride. Anyhow, this is the culture that grows the bacteria that they test. So this is the Petri dishes and this is what you're looking at. So like I say, the areas of clear means that this antibiotic is working, and this antibiotic is working. So you're really in luck with more than 2 antibiotics that work. Today, you're very lucky. So here's something else. So most men have a prostate biopsy. Everybody that doesn't know what that is, it's basically 14 needles that goes into your scrotum and takes actual skin samples, tissue samples, and then they analyzed how mutagenic it is, or has it been changed? Does it look irregular in shape? Charlie's nodding himself. So I'm a kind of person that when I go see a doctor, I usually get into either an argument or I'm very polite. Well, my urologist says, well, you're in great health. You have zero sign of cancer. You have no sign of prostate cancer. He says, but we really recommend getting a Gleason score. That's these needles that go into your prostate. And I says, I'm not going to do that. I don't want to do that. And again, I'm thinking the infection risk is a real one. Oh, he said, no problem. They give you antibiotics before you even get the biopsies done. I'm like, well, how do you know what antibiotics to give me? Whoops, I don't know. He was, luckily he was in a good mood, and he was, and I says, what about the other problems with this? And so I started listing all the problems with it. He says, well, you can get an MRI. We have a 3 Tesla MRI if you want to do it. I said, yeah, let's do that and look for. But yeah, that's where we are with him. But he's like, well, you can't get any more MRIs. Your insurance company won't pay for it. So you need the Gleason score. That's our gold standard. So I'm not doing the anyhow, just a little interesting. So MYCIN was originally developed in the domain of bacteremias and then included meningitis. Okay. So what this is, a backward chaining, if you can think of what backward chaining is. So you have basic output that you're looking at, and then you have a series of rules that's built up to do a diagnosis of what the like I say, the identification of the bacterium. And so you have to take in all these other situations: clinical trauma, neurosurgery, host factors, immunosuppression, age, and usual pathogens that contaminate. Candida is one of them. Selecting optimal antibiotics. Okay, so this is the heart of MYCIN. It was built in LISP. Anybody know what LISP is? You guys are a bunch of old people. You didn't have to work on that, did you, Charlie? A little bit, yeah, same here. Okay. So anyhow, this is what this thing. So I went to my books. I don't throw any of my books out. So this is a book I had to analyze in my master's program in Chicago. And my professor said, I want you to read this and study this book, and I want you to analyze the book. And I want you to go peer-reviewed sources and give me a full analysis of this book. Look how thick this book is. So this is a book written by Dr. Buchanan and Shortliffe, the 2 authors, primary researchers on MYCIN. So this was done at Stanford University, the biggest project of its time. It started in the early 80s, 84, 83, 84 it started, but it went for approximately 10 years, 8 to 10 years, the actual project. I don't know how many millions they spent on this project, but it was a big deal. So they had not only computer science people that knew LISP at Stanford writing the rules engine for the MYCIN, but then they had the medical staff at Stanford, the professors that were doing the medical diagnosis, checking over, actually supplying the rules. So what did we call the rules being supplied? That's your knowledge acquisition. So you built rules, and this wasn't supervised learning, we'll get into that, but so these are explicit rules that have to be generated that gets into the head of, they call it knowledge acquisition, is the phrase they use. They had to get it in the head of the medical professors at Stanford. And the net of this whole thing is this massive book that I had to read for my master's degree. So this is going through my mind when my pet cat is dying, and I'm thinking, wait a minute, didn't we? I remember doing a book analysis on for my master's project that we solved this problem. We sped up the whole diagnosis and identification, and you know something? We didn't. This is an epic failure. This is an epic failure. And I'll get into some more reasons why that was an epic failure. So the 84 it is. So I put my notes on the bottom of the references I'm using for this thing. Again, it's a LISP rules interpreter. So it actually, you build the if-then rules in your knowledge base, and then you have a user agent that would do the client interface, where they would present case, observation, symptoms, and so forth, environment. And then you'd have a domain knowledge base, which is really a rules-based knowledge base. So you get the idea that there's a lot of problems. And when you read this book, they even acknowledge many of the problems that they ran into, like they call truth maintenance. So what happens when you have one rule or two rules that contradict a rule you did 6 months ago? So you have rules, maintenance, and truth that you have to determine what's true about it when I have conflicting rules. How do you identify conflicting rules? Okay, so that was one of the big things they identified. So here's what I went for. So I said, what was the statistics of their own data? So they're biased, right? They're doing their own testing at Stanford. And they ended up finding 65% of MYCIN's prescriptions, that's their recommendations for treatment, was rated acceptable by the evaluators. Now, this is during the MYCIN project. And again, these are highly biased people. So the corresponding mean rating for the 5 faculty was 55.5, ranged 42% to 62.5%. And then the hypothesis was each prescriber was rated equally by the evaluator is rejected. Okay, so that's the standard hypothesis test. So basically, the best it's going to do at the time they built the system with access to the developers, they got 55 mean, 55.5% was the mean of the range. So right away, what jumps out at you, right away? Okay, this thing is identifying a critically timed system. So first thing I asked for, what's your sensors? No sensors, just observation. Okay. Yeah, no electronics. This is not an embedded system. This is people entering medical information. Well, anybody that's seen what doctors put into the input on this thing, now you start understanding why this is not a formula for success. And but I'll get into that. All right. So consensus was they only had 10 cases, and the evaluators came up with 70% where therapies were rated as acceptable by majority. First of all, that's, for medical applications. Is that good enough for you guys? I mean, this is terrible. This is just a total disaster. So you get the idea this isn't going to be used in production. So 8 years later of academic research, this barely went into production. Oh, there was a few cases. Every one of the cases I read were considered failures. And yes, unless you look at one of the early 1 or 2 cases that they probably read this book and said, yeah, this is a success. But anyhow, it's been known as a and here's what I was saying. So MYCIN, the rules prescribe penicillin for a case of meningococcal meningitis, as did 4 evaluators. Again, this is 1984. Well, penicillin must have worked, John, in 1984. It doesn't work today. Okay, so rules was the craze in the mid 80s. I'm running a network communication network for one of the largest insurance companies in the US. And so I had access to all the IBM tools. So IBM came up with their own copy of MYCIN, which was open. You put your own knowledge in, right? So I brought it into our network. I was running the network for CNA Insurance. And we said, hey, wouldn't it be great to put a network diagnostic system with the rules engine called ESC? This thing ran on a mainframe, get some idea. So that's what I did. So I worked on this thing. And right up front, I'll tell you what depends on what your criteria for success is. Because if you assume that my network operators and my network diagnostic technicians and engineers are going to use this on a continual basis, you'd be wrong. If you say, did they learn anything from it? Yeah, I think it's great learning. You know, here's a query system where you can query that I'm seeing this system on this node in this location, and what was the first thing I do to diagnose this node to see if it's still operational and the network path is complete? Well, you have things like you put it in loopback. So there's a whole series of steps you do for network diagnostics. And so my people did these things. And when they didn't know what that was, this would be great for educating it. So my people, I told them, take a look at this, tell me what you think. Several of them said, this is interesting, but I wouldn't use it again because I know I got the answers now. I know how to do network diagnostics by now. You know, this thing had a couple hundred rules in it. Now, for a newbie walking into the Network Operations Center at CNA, it may be the best thing since sliced bread for 6 weeks, you know, or a few months. Anyhow, so this is the good news is I got all kinds of awards for it as a network diagnostic, backward chaining rules, systems to network. And it worked. Like I say, it worked. It wasn't a long-term tool. So the 80s was one of expert systems. So if you look at, is anyone familiar with Google's Ngram viewer? Okay, so this does a statistical probability of what people search on. So we look at what's our AI. Well, you can see a slow rise of AI from 1980 to about 1960 to 1980, and then a sharp peak where everybody's building expert systems, you know. I had also worked at General Electric, and that was the big thing, to diagnose locomotive failures in the field with no human technician available. So these monster locomotives that are traveling somewhere in the world, they built a system where they could do remote access to the locomotive and get inside the engine and look at all the sensors that's sitting in the engine. And that puts it in a little different area because the sensors were all there in a huge locomotive. And these required, the EPIC system required an operator to put in this case, a bacterial infected required a medical doctor to put in the symptoms. And in this case, it's doomed for failure. So you see a big peak in the mid 80s, and then it starts slowing down in 1990. By year 2000, you've gone through, that's the first AI winter. They call it the AI winter, meaning AI is the best thing since sliced bread. AI is useless. By year 2000, AI, and I can build an expert. Oh, no. People don't do that anymore. Anyhow, then comes along 2011. You had a machine winning Jeopardy with 2 Jeopardy award-winning experts. So 2011, they won the WATSON supervised learning large language model. Starts getting to what we see today. But anyhow, and massive amount of CPU cycles. I mean, they were throwing, I would say, I saw 80 million somewhere was what IBM put into this. So they won Jeopardy. Now, what good is that? Well, what's great about that is now I could take this, replace the Jeopardy knowledge, general knowledge, right? So they're establishing we can beat humans in a general learning model with Jeopardy. I can see more general. But anyhow, so let's go to, let's offer oncology advice. Let's solve cancer. Hey, man, this is, and here was, I remember watching the ads in 2011. So I'm watching this very carefully, and they're promoting the hell out of this thing. And so in medical diagnosis, especially cancer, I don't think we have a handle on cancer. I mean, what they call cancer, curing cancer, they don't cure it. What they do is they'll give me, if I was suffering from prostate cancer, they would say, look, we're going to do all the surgery and we'll give you another year on your life. for 6 months on your life. So their metrics, and I talked to my my doctor, and I said, what do you use for metrics? He goes, how many days we can keep you alive after prostate cancer is diagnosed? What is the, because it's gone into metastasizing, blah, blah, blah. But then he says, our final metric, our goal is to keep you alive for another months, year, hopefully a year or two. Anyhow, so they don't have any, you say, is that a cure? No. So what, you're going to throw AI at it? Are you going to throw chat? Yes, that at this supervised learning system? Well, how are you taking supervised learning from an imperfect source? Anyhow, I'm jumping ahead a little bit. But anyhow, so Watson, 3 years after IBM selling Watson to recommend cancer treatments, the academic reports are coming in. This is a failure. This is terrible. Worse than terrible. And I'll go into that. So the supercomputer that they're using for Watson isn't living. It's still struggling with the basic step of learning about different forms of cancer. Well, guess what? Okay, I'm not surprised. Only a few dozen hospitals have adopted the system. And again, IBM's paid almost 100 million, 80 to 100 million on investing into a whole new division. They built a whole division around Watson. So IBM wanted dominance in the AI business, so they sunk all this money in. Foreign hospitals, physicians complained that this device is a bias towards American patients and methods of care. Okay, that's a biggie. I mean, because you know, this is not your globally recognized cancer cures. That's what you're discovering, is that doctors can't classify cancers correctly. They can't determine what the cure is correctly. We're in a dark age of cancer. I'm sorry. I hope there's any doctors in this audience, medical doctors. This is not good. Only a few dozen hospitals had adopted Watson, which is a long way from IBM's goal of establishing dominance. So I like this source, Stat News. Stat examined Watson for oncology's use in hospitals across the world, and that's how they got the data. And if this sounds familiar, this is really a huge effort for solving oncology solutions, you know. But here's the thing, it's a supervised learning, natural language, large language model that's used in this thing. So now think about this. So you got the good and bad and ugly doctors, right? So how are you gonna determine the truth of this data? I can tell you exactly how I do it in my talk tonight with embedded systems. I have sensors that I calibrate and I measure, and I know exactly what's going on. IBM executives acknowledge Watson is in its infancy. It's improving rapidly. It should for 100 million. They will offer guidance about I don't know how many doctors you know that have plenty of time to look for guidance about treatment for 12 cancers that account for 80% of the world's cases. They said it's saving doctors time and ensuring that patients get top quality care. They're not selling it. They're not buying it. It's just not buying it right now. So let me just go through here. So here is my takeaways on this thing. Your sources on both systems, the rule-based and all the analysis, I can tell you what the academics have said, what the flaws were. So the number one flaw, by the way, the number one flaw, the showstopper in medicine is lawsuits and insurance companies. That's your showstopper. So you have a father that died of bacterial infection that you didn't know for 4 days, 3 days. And a lot of people don't have 3-4 days. My cat didn't have that much time, and they extended it. They didn't even deliver the results. So I'm done with Carnegie Cat Hospital. But your sensor is humans typing this stuff in. Not going to work. So it can't solve slow sensors. So what are we doing with the Petri dish? 72 hours, 3 days, it's too slow. I need an answer now. So what's going to give you an answer quickly? Well, somebody has to do an improved sensor design. And Kerry Mullins did a huge breakthrough. In fact, he got a Nobel Prize for it, for identification using the polymers PCR amplifier, polymers chain reaction amplifier. So it's an amplifier. So he can identify the strain, the unique genetic strain, and then map it into a database. Now, what he said before he died, young guy, I don't know, he said you can't use it for low level of virus identification, where you need an amplification. Amplification in a PCR is number of cycles of heat, cool down, heat, cool down. It goes, so it's growing this, right? It's growing this, making copies of this genetic structure. And then you're sensing, he says, you have to do and he was talking about the AIDS crisis. He died probably at the end of towards the end of the AIDS crisis. But he's saying these idiots in Washington are saying, use my PCR as a test for the AIDS virus. And I heard his speech on this. This is pretty amusing. He has no use for the federal government, but hey, that's a different story. And he says these idiots in Washington have got this thing to identify an AIDS virus, have to do a 40 times multiplication, 40 cycles to heat, cool. And he says, you want to know something? I can find it in any person on Earth. I can find the AIDS virus. If I multiply times 40, I can find it in anybody. It's there. It's inert. It's not doing anything. It's in the body. And he says, and their treatment for AIDS, and this is really important. Their treatment for AIDS is, what was the treatment for AIDS? AZT. And you can't buy any other treatment. You can't go to a doctor and get a different treatment. You have to, we will pay, the federal government will pay for AZT, and that's it. He says, well, that's kind of curious. All the data I've seen on AZT is killing people. This is by Kerry Mullins, the Nobel Prize winner of PCR technology, amplifier technology. Anyhow, it's kind of crazy, but, and then he mysteriously gone. I don't mean to be paranoid, but maybe I am. Okay, so you can't replace doctor's notes, technician notes, nurse notes with actual classification unless you clean up the data. Now, how do you clean up the data in this? I don't know of an easy way. I don't know an easy way to clean up the data. Now, your whole heart of supervised learning, which is included in our latest systems, are supervised learning, is only as good as the data records, the medical records that the doctor, nurse, technician is keeping. If that's flawed, guess what? Your data is flawed. So how much of this data is flawed? I don't know. So Watson was a lot of the failure was its low percent accuracy. Okay, number two, I have the medical data input and classified by humans as a flawed process. Okay, so let me just say it. So there's other than this book I brought in from my master's library, this was an interesting story. So these two authors are both medical researchers, and there's a book out called The Perfect Predator. I recommend everybody read it. So, beautiful couple, tons of money. They go on vacation. Where do they go for vacation? They go to Egypt. The man decides, Thomas decides, Patterson, he decides he's going to go into, some of the tombs in Egypt. He's going to go do some exploring, climbing in the very narrow areas. So wouldn't you know it, the next few days, 2 or 3 days later, he's sick. And they're on vacation, they're in Egypt. So he comes down with some infection, right? Goes to the doctor. The doctor gives him antibiotics. They don't do a damn thing. So then he goes up, he says, well, we got to fly you into the States. And now, again, these are research physicians that are experts in biomedical therapies. And so Thomas is suffering. These people he's going to die. He's gone twice in the coma while they're trying different antibiotics. He's in coma, almost dying. So they're trying all these solutions. They got contacts at all the California hospitals, research clinics, the government's medical lab, research labs, the government biowarfare labs, and they got this guy's dying. He's going to die. So it came to the conclusion after about 6 months of him in the hospital in coma to try the new phage. Now, what's a phage? Anybody know what a phage is? Okay, so phages are viruses, but they only attack and eat bacteria. So they're very convenient. If you match up the phage, they don't eat all bacteria. They like they're different strains of phages or viruses that like different bacterium. So you still have to identify the bacterium, and then you have to figure out how to get your hands on some active viruses that are hungry for this bacterium called phages. They don't attack people. They're very safe. There's tests I've done in a lab where I've used phages, perfectly easy to handle, and there's no reason they're going to attack you. Anyhow, so they have solutions to save this guy's life. It was a phage that they got from a military biowarfare facility in this country. Saved his life. He would have been dead. He was already in coma. His body shut down several times. Anyhow, but this is an interesting story because this is true, and it's by two very, very competent, educated professors of medicine that lived through this thing. Okay, so we need to pursue phage virus solutions, and we need to automate it. The system must be bounded, embedded, and fully automated. Now, what I mean by that, I'm going to go in a little bit detail on the embedded stuff. Are we out of time? What time is it?
It's 11.
11. Okay. What time is it now?
5 minutes to 11.
Okay. All right. So I'm going to get into number 4, which is the system must be bounded, embedded, and fully automated. The assumption that you're going to use supervised learning is that your data is accurate and delineated and bounded. And that's where we see the big successes in AI. And that's where my speech is, what I see as a huge revolutionary change in the societies with AI. But we don't call it, I mean, you shouldn't call it general AI because this is not the answer. Okay, so the system that isn't bounded, like doctors entering thing, that's the data's bad and poor classification, and there's enough problems with the classification for the insurance, let alone using it to train an expert system. Legal constraints. So, okay, the lawsuits have started already with both of these systems. So the lawsuits about, you treated so-and-so, they died a nasty death. We're suing you because you used your computer to make the decision. Really? Diagnosing and treating cancer does not currently have cures, but time modulation. Okay, so this is the idea that we're not curing cancer, we're changing the time you're alive. And again, supervised learning systems require expert cases to learn from, and testing AI systems remain limiting, So I'm gonna, if you got any questions, I'll take questions now, but the other thing is I'm going to get into what makes a successful system with the short version of what's successful. Yeah.
As I understand it, the reason why antibiotics, which used to work, no longer work, is that the bacteria against which they were once effective have undergone Darwinian evolution.
Exactly.
Fortunately enough, public media, they don't want to use that term for obvious reasons.
Well, they've definitely evolved. They evolve. I don't even think that's a contradiction of anything that you're hinting at religion or anything. But to me, it's evolving. You have a mechanism
throughout the entire COVID pandemic. These new strains kept occurring.
Mm-hmm.
I did not once see in a public medium a reference to evolution as accounting for the popping up of new strains. I don't know why. They never said that.
Oh, yeah, I picked it up on a few places. It says it's
But maybe a scientific.
they call it a new strain. By definition, it's evolution. You know,
Well,
if it's a new strain, it's evolved. I mean, maybe I'm reading too much into it, but
they never use the word.
yeah. Bacteria is actually, if you look at it, they have they have a slime that they can protect themselves on. They can modify how this protective shield works. They work as a team. Most people don't know that. There's a famous, I think it was a Nobel Prize they won in Princeton, a university professor came up with this idea of bacteria work as a team. They communicate and work as a team. Yeah. So it's almost a directed evolution because they're working as a larger than single cell bacterium. This is a it works as a team. I could get those references if you're interested. You can contact me. But any other questions? So let me tell you where I'm going with a successful system. And let me go. I'm going to go through this real fast because it's my speech this afternoon. But I'm just going to show you what works. Okay, here, airbags, for example. They never talked about airbags. You know, airbags was developed in the 70s. And now a typical airbag is maybe 10 airbags in a new car. If you go to buy a new car, I don't know how many is in a new car, Charlie? I don't know, lots. Side airbags, obviously driver, pay.
There's an English 8 or 10 or 12.
10 or 12? Wow.
Yeah, because it's for passenger on the outside side. So
Side.
on the side. So,
Yeah. Yeah. So 1998, I've established where they're using neural net embedded systems to put this into their airbag controller. So there's an airbag controller that detects crash. How do you define a crash? Yeah.
Very high acceleration.
Right.
Along one vector.
Exactly, a deceleration on one vector. Negative acceleration, right? Deceleration. But
I remember general relativity.
well, you're exactly right. Now here's the other problem. You know what else falls in that category? Potholes. You hit a pothole. You want your airbags to go off? What if you have your kid in your car next to you? Airbags go, oh, there's a percent, you know, severe injury or your mother is fragile and 65 pounds. You don't want an airbag going off. So since now this is 1998 is where they first documented. Why did they wait so long? This wasn't found in academic literature that embedded system being used for every airbag controller. You don't find that in the why wouldn't you find that in the literature, academic literature? This is all the secret sauce. This is General Motors secret sauce. This is Ford secret sauce. When you deploy the airbag is the family jewels basically of automotive engineering. And I first got educated in this. I was talking to the project manager at Analog Devices. So they ship, I don't know, a couple million accelerometers per week into the automotive, and they go into airbags and everything. And he says, you know, this has all been a big kept secret of when they deploy it and how what data they train it on. This is a form of a neural net, a convolutional neural net. And there's a team of people at all the big automotive manufacturers that are always working on the next generation of crash detection and prevention, injury protection. So I pulled this from one of the earliest academic document, was the steps. So they call it neural networks in the 90s. And they train it on different data, and they have to, in order to test the viability of it, they had to keep parts of the data where the trained data is not seen. And then they show it the trained data and see what the response is. Because you don't want to fire the gas for the airbag. You just don't want to fire that. But you do want to fire it quickly if it's needed. You know, so this is what's gone into the system. But like I say, there wasn't a lot of celebration on this because they didn't want to know, they didn't want their competition knowing how they were doing this. But this is an actual flow chart of what they were using in the 1998. And let's see here. Let me just tell you real quickly here. So here's a cargo sensor. So what do you want to do with you know, the logistics chain really controls everything. Food production, everything. Distribution, obviously, of food, cold chain. So what do you want to know? You know, you got 53-foot trailers. Some of them are a little bit longer, but you have reefers and non-reefers. You have refrigerated for foods and so forth. But what you want to know is your cargo. You want to identify cargo shift. So if you look at this diagram on the right, you see the box, the skids are all in a big mess. You want to identify, but you want to identify if it's empty, right? The second my load is now empty, I've filled up 4 Walmart stores from DC distribution centers, and now I want to see what do you got? What do you got coming back? Nothing. Okay, that's called deadheading. You don't make money with deadheading. But having a smart cargo sensor to actually look at the image and say you have nothing in here, you have no skids, you have no empty skids, you have nothing, and now I can go and I would know what the percentage loaded. So this is what type of equipment needed to unload, because I can look at the skids and I can determine, and I can, of course, I got GPS tied to this, so I know exactly where my load is, what the type of load is, what kind of, like I say, characteristics. And I've taken this from Powerfleet slides. So I know my buddy is actually did all the software for this thing, and he did the hardware, a lot of the hardware with an Israeli team. He worked on the hardware, and he was saying we used a lot of these patents for optical recognition using convolutional neural nets. So that's what's in this LV710. The difference between the medical and this, the sensors are well trained. They know exactly. They're trained on boxes that are disorganized versus straight line organized boxes. They can quickly do a percentage load. They can actually tell if the door's been opened. You know, they can look at things like the door open, because it's actually has a wide angle view, and it's looking at the door too. So we can look at humans present, which is kind of interesting. You can identify the regulars who come in and the regular people that steal things in south of the border, let's say. There's a funny story with, I worked on the cargo sensor for Walmart's trailer. I was working for General Electric at the time. And we were tracking all these assets. We had this whole GPS, we were using satellites, so we could go, they go anywhere in the world. They go deep into Central America. We could still track them, no problem. And so we're looking at all this data. Why are all these trailers stopping at this point in Mexico? Well, they're being hijacked. And and the logistics manager at Walmart telling me to my face, he says, well, we got to deal with them. They can only take so much. Certain time of day, it's predictable there's going to be a delay at this border because they're stealing. Anyhow, but the whole thing, all the money for the contracts for smart cameras was based on logistics, not security, which is kind of surprising. Now, that was a few years ago. I don't know what it is now, but this is currently in production. Unlike the medical applications we talked about, this is in high volume production. This is being used every day, every hour in production. So there's a big difference. Am I out of time? Good. We got
2 minutes.
Okay. And but anything I just told you is that it's well bounded. We understand what the sensors are delivering. Unlike technicians, nurses, doctors, and they're given biased information to begin with. And during you mentioned the COVID situation, the records, if you fill out the records correctly, you get a $35,000 bonus payment if your patient is suffering from is COVID. Now, the fact that there's at least 3 comorbidities they're dying from has nothing to do with it, because you don't get your $35,000 from the government if you don't say put COVID on the form. So all this data is bad. You know, it's got to be checked. It's got to be reviewed. You got biases in the system. And then if you, by the way, if you have a patient you diagnosed with COVID and you talk that patient into getting remdesivir, that's another $10,000. So you get almost $50,000 if you can fill the right form out, the right data forms.
Cost.
Money, the only money here, John. You know, people aren't interested in more money, right? You know, and that's why they push. If you go to a hospital, by the way, they push remdesivir on you because of the bonus, the cash bonus. Anyhow, I'm gonna get off the target. Okay, any other questions at all? So if you wanted to see this other stuff here about bridge monitoring and ultra low power pest detection for smart agriculture, really important in apple orchards, for example. That's what I'm going to talk about this afternoon. So you can, but the difference is these sensors are accurate. I can calibrate them. I can identify the data is good, and I test it. The data is good. AI isn't as good as other systems where I can't do a firm statistical, but I can at least have it look at unclassified data. Like when I first started checking ChatGPT, I started typing away, asking known questions like, what's the equation for receive sensitivity on a particular set? So I got really a bogus answer. This was ChatGPT 3. They say 4, it's going to be better. So the one thing that's nice is to ask the same question again. So I asked it 10 times, I got 10 different answers.
Apparently, a lot of the problem has been in identifying the species of bacteria.
Right.
How effective is it to just get it on a slide and look at it under the microscope? Can a good microscope?
Well, I think that's a good point, is because photonics has gotten to the point where you can do extreme magnification. You can do filtered light. You could say that this shows up under UV lamp filters. No, I think photonics is the answer. You could do a sensor with photonics, like the latest dust sensor, 2.5 micron or less. They use lasers. They use laser lights, and they look at clouds of particles.
Trained eye.
I don't know what's required there.
Are there people?
Well, you can't do genetic sequencing with your eye.
Look at the bacteria microscope. Oh, this is a.
Well, the mutation might be. You know, you're gonna have to get into the structure. You know. Anyhow, I hope you enjoyed it. Thanks, guys.